And Dhruv, I see from your note that the remotes can actually usefully get Aijen's feed. So Aijen, if you want to turn on your video, you're more than welcome to. And we're going to
Okay.
get started now.
Okay.
So can the folks in the back of the room please confirm that I'm audible? I want to make sure the volumes, they say it's good. Okay. There have been problems with the interaction, microphones, masks, audio settings. Thank you. Okay, this is the SAVNet working group. Thank you all for coming. This is a new working group. We're going to work through the presentations. Before I turn it over to Aijen to go through the chair's slides, I want to make one point. I have been asked to remind, it looks like everybody got the message, but I've been asked to make a point of reminding folks in meeting rooms, masks are required. So it looks like everybody got that message, but I had been asked specifically to issue that reminder, so I have done so. Aijen, you're up.
Yeah. So I should share my screen. Yeah. Can you see my screen now?
You don't need to share. I've got the slides up.
Okay. So I will first I will introduce the status of the working group and the agenda of this
You
meeting.
need to speak
So
up
first,
a little bit. Speak a little more slowly and speak up a little bit. We're having trouble hearing it a little.
Okay. So first I will introduce the status of our working group and the agenda of this meeting. First is the note view of the meeting. So this is for the reminder for the IETF policy in participating in the meeting. The important thing is for the participant to notification the patent to sorry. So I will introduce the working group status and the approved charters. Our working group was approved in June of this year. That is last month, and it chartered to the following item. The first is the problem statement, use case, and requirement. The second is the SAVNet architecture document, and the third is the definition of a routing protocol, independent operation and management. For the problem statement, we will analyze the current solution and their limitation for the intradomain and interdomain. And this item may not be published as a IETF stream RFC, but may be just maintained for a draft for the reminder for the newcomer. And for a second item, we will define one document for the intradomain survey and for the another for the interdomain survey. And each document must describe the condition under which the architecture may improve accuracy or performance with respect to the existing saving mechanism method without assuming the pervasive adoption. That is, the method should be adopted incrementally, and each document must also include the privacy analysis and the threat model addressed by the proposed architecture, and comparison for the existing saving mechanism. This is the requirement for the saving architecture document. And the third is for the definition of the some operation and management, which should be independent of the underlying protocol. And after our working group finishes the or reach consensus on this item, we will discuss about whether it is appropriate to continue with further work, must work. So we will discuss based on our conclude items, and during this process, we will coordinate with and collaboration with other working group. For example, the LSR and IDR the working group. Okay. So this is the planned milestone. The first we will adopt the problem statement, use case, and the requirement document in this year, November of this year, and then adopt the Interdominant architecture document. At the same time, we will begin to discuss the Interdominant and adopt it. After that, we will begin the work for the operation and management of the Interdominant and the Interdominant network, and we plan to finish our work at 2025 March. Okay. Next, please. Yeah, this is the draft agenda for this meeting. After my introduction, the Dan Li will introduce the problem statement for the Interdomain, and Lan Chen will introduce the problem statement and use case and requirement for the Interdomain. And after that, Joe will make the working group stage planning based on the presentation and the discussion. And after that, we will discuss briefly the two proposed solution. For the first is from the IGRA, and the second from Yuanxian Qiu. Okay, this is the current status and the draft agenda for this meeting. Okay. So if there is no any question for the agenda and for the status, can we please begin the presentation?
Okay.
Okay, can you hear me, Joe?
Yes, we can hear you, and I have handed you control over the slides. So go ahead, you have the slides.
Okay. Thank you very much. Good afternoon, everyone. I'm Dan Li from Tsinghua University. Welcome to joining the first SAVNet working group meeting. I'm sorry that I have to be remote again, and I hope I can be on site in the IETF meeting in the near future. So today, my presentation is about Interdominant SAVNet, gap analysis, problem statement, and requirements. Let's first introduce the background knowledge. We know that source address validation.
If Aigen turns off his camera, Dan Lee can turn on his, and then other people can see.
Okay. So can you see the video from me? Yeah. So I will continue. Source address validation, or SAV, is important for defending against source address spoofing attacks, especially about reflection attack. Since the year of 2014, the Malus initiative is calling on network operators to implement SAV as close to the source as possible. However, the number of access networks is so large that we cannot depend on every enterprise network to deploy SAVI, which is a host level source address validation. So when an access network does not deploy SAVI at the source. Interdominant serve can help block spoofing packets. So it is necessary to run interdominant serve in the internet. The current practice of interdominant serve mechanism is primarily ingress filtering. Ingress filtering includes both ACL-based serve and strict URPF. They are defined in RFC 2827 and RFC 3704 respectively. For ACL-based serve, it just manually configures the filtering rules to specify which source addresses are acceptable. And for strict URPF, the router looks up the source addresses in its local FIB and requires that the incoming interface be the same as the corresponding forwarding interface. There are two other alternative implementations of ingress filtering, namely feasible URPF and loose URPF, but they are not suitable for interdominant serve due to their overly loose validation. This figure shows a typical adoption of ingress filtering in an interdomain network. There are 6 routers, namely router 1 to router 6. In this example, router 1, 2, 3, 4 directly connect to a subnet, while router 5 and router 6 do not connect to any subnet. Specifically, subnet 1 simultaneously connect to router 1 and router 2. Subnet 2 directly connect to router 3. Subnet 3 directly connect to router 4. So router 1, 2, 3, 4 run ingress filtering and the interface which connects to the subnet. And by running ingress filtering, the spoofing traffic which may come from subnet 1, subnet 2, and subnet 3, which if this traffic spoof their source addresses, they can be blocked by the 4 routers. Okay, next, let's analyze the gap of existing interdomain serve mechanisms. The first gap is improper block. Let's focus on subnet 1 in this example. Subnet 1 simultaneously connects to router 1 and router 2. Let's assume that the prefix of subnet 1 is 166.0.0.0/15. However, subnet 1 advertises half of its prefix to router 1 and advertise the other half of its prefix to router 2. But subnet 1 can originate traffic with the source address of whatever address within its prefix scope. So in this example, there will be routing asymmetry in router 1 or router 2. So if we apply strict URPF in router 1 or router 2 to implement ingress filtering, there will be improper block. And if we apply ACL-based serve to implement ingress filtering, we have to make manual update if there is prefix update or topology update in subnet 1. Therefore, there may be improper block if we run ingress filtering in a multi-homed subnet. This is the first gap. The second gap is the vulnerability in inbound direction. In practice, spoofing traffic may not only come from the subnet of an interdomain network, but can also come from outside AS. In this scenario, let's suppose that router 5 receives traffic coming from outside of the AS, which spoof the source addresses of subnet 1, subnet 2, and subnet 3. In this case, by running ingress filtering, there is no chance for router 5 or other routers to block this traffic because ingress filtering only checks traffic originates from the subnets. So this is the second gap. That is, ingress filtering cannot work for inbound traffic. The third gap is misbehaved router. Let's suppose there are two possible cases for misbehaved router. In the first case, if router 4 is compromised or it cannot strictly conduct self mechanism, then the spoofing traffic from subnet 3 cannot be blocked by other routers, such as router 6. Or let's suppose another case, that is router 5. If router 5 is compromised and originates spoofing traffic, then this spoofing traffic cannot be blocked by other routers either, such as router 1. Therefore, ingress filtering cannot help if there is a misbehaved router in the interdomain network. This is the third gap. The fourth
Before
gap.
you continue, Dan, Jared, you had a question, so go up to the mic. Please speak very close to the mic because it's likely to be a general remote problem.
Yeah, if you can go back one slide to gap number 3.
Yeah. This one.
So are we trying to consider compromised routers as in scope?
Yes, we try to.
I don't think that's feasible.
That is something we need to be explicit about in the work we do on the gap and on the requirements. We can decide either way, but we need to be explicit.
Yeah, I think that, considering compromised routers as part of in scope is going to be incredibly difficult as part of this, because at some point you have to have trust in some network element. And going and defining what network elements are trusted versus untrusted is going to, I think, be incredibly hard, because especially in large organizations, you may have different people with different information around, who know about configuring the network elements. And some people may think something, they may have a perception that something is misbehaving or compromised that it actually is not, based upon that behavior. So I think we have to be very clear around how we define this, and if we consider this to be part of in scope, because once you have things that are compromised, you lose all the basis upon which to base any of your decisions, any of the subsequent things. If my computer is compromised and has malware on it in the UEFI boot ROM, I can't trust anything beyond that point. And so I think we should just, be very clear and say, yeah, if the device is compromised, it should just become completely untrusted if that's the goal here.
I think it will be important to make sure we spell out what we are doing in that regard, whatever it is we want to do. Okay. Thank you, Jared.
Yep. Yeah. And then the other thing is on this router 5, router 6, the devices, they're probably not originating the spoofing traffic unless they're have something in their ASIC that's generating the packets, but it could be that they're transiting traffic that appears to be spoofed. And I think we need to be very clear in how we talk about this, because I don't believe in this example that you intend to say that the router is originating the traffic. I think you mean that a router is transiting this traffic, and in transiting it, it may be that router doesn't have knowledge that from subnet 1 that there is an alternative path to exit that, by which router 5 becomes aware. And we get to, this is one of the concerns I have in this entire space, is that you're trying to describe all of the feasible network paths, including all the backup paths, failure condition paths, and such. And I think that this is going to be very hard for this working group to undertake that effort. Is that a lot of these things, they will look like they're compromised. They'll look like some other behavior. And it may just be that it's not a steady state behavior. It may be that it's in a state where some network element is failed, that's how the traffic appears there. But around this word originates, we absolutely have to be clear there, because I don't believe that you mean that router 5 is generating that traffic.
Okay, we will make sure the minutes include that this issue was raised so that we do track it going forward. Dan, go ahead.
Okay. Thanks, Jerry, for the comments. I think okay. This is arguable, and we can make more discussions later by discussing the third gap about the misbehaved resulter. Actually, we just talk about the resilience of any solve mechanism. Okay, if some router just cannot work correctly, whether we can have some alternative way to make up it. So this is the general consideration. But of course, we can make more discussions later. Okay. Then I move to the fourth gap. That's about the misaligned incentive. Okay. Let's consider a case where router 3 and router 4 deploy ingress filtering, while router 1 and router 2 don't. This is possible. For example, in China Education and Research Network, we have a single AS, but separated into several campus network. So it is feasible that it is possible that maybe some campus network deploy ingress filtering, while some other campus network do not. If under this scenario, we just consider a case of a reflection attack. The attacker is located in subnet 1. The victim is located in subnet 2, while the reflective server is located in subnet 3. The reflection attack is like this. Subnet 1 originates the spoofing traffic towards subnet 3, which forges the source addresses of subnet 2. So in this case, the spoofing traffic can be successfully sent towards the reflection server, because router 1 and router 2 do not deploy ingress filtering, while router 4 just checks the ingress filtering at the interface, which directly connects to router subnet 3. So in this case, even though subnet 2 deploys ingress filtering, it cannot prevent its source addresses from being spoofed by subnet 1. So generally, it means that the deployment of ingress filtering only guarantees that the deployed subnet cannot send out forged traffic, but it cannot prevent the deployed subnet from being attacked by reflection attack from other subnets. So there is a misaligned incentive for the subnets to deploy this Interdominant solve mechanism. So this is the fourth gap, misaligned incentive. Okay, next, let's discuss the problem statement. Based on the gap analysis above, we think there are three general problems for existing Interdominant solve mechanisms. The first problem is inaccurate validation. The problem is that existing Interdominant solve mechanism may cause improper block under asymmetric routing. And the reason is that ingress filtering only conducts solve based on the local fib of the routers, which may not match the real data plane forwarding path from the source. The second problem is limited protection. The problem is that existing interdomain solve mechanism fails to block spoofing traffic from inbound direction or misbehaved resulter. Okay, maybe misbehaved resulter is arguable, but okay, it cannot block the spoofing traffic from inbound direction. And the reason is that ingress filtering only works for traffic from the directly connected sublets. And the third problem is misaligned incentive. The problem is that existing interdomain solve mechanism suffers reflection attack even when the solve mechanism have been deployed by the victim. And the reason is that ingress filtering only constrains the behavior of the deployed sublet rather than protecting the deployed sublet from being attacked. So these are the problems for existing interdomain solve mechanisms.
Okay, before you continue, Dan, Tom Hill has a question.
Okay.
So, Tom is coming to the mic.
Hi, Dan. Tom Hill from BT. In regards to the problem statement and the situations that you described in the couple of previous slides, there's an indication on here about undeployed and deployed routers, and I just wanted to confirm, in the situation where we're talking about intra-domain, does undeployed mean that no one has configured any form of existing source address validation?
Mm-hmm.
I think that's correct.
Dan, did you hear the question?
Yeah. Okay. Can you repeat your question? I want to confirm I get it.
Okay, no, that's fine. So in this example, this is one domain. This is a domain where we manage all of the routers ourselves. They're all our routers. And some of them have source address validation deployed, and some of them do not have source address validation deployed. Why couldn't you deploy source address validation on all of the routers?
Yeah.
Okay. I mean, I'm thinking about the scope here is like, are these problems that actually exist, or is it someone is in charge of all of these routers, but they haven't configured them all properly?
Yeah. So the case is that let's just use Chela Education Research Network as an example. So it is an interdomain network with a single AS. Its AS number is 4538. This is a single AS. But this interdomain network is separated into multiple campus network. So part of the routers on the subnet are just operated and run by some campus network, and the others are just run by other campus networks. So since these different areas are managed by different campus networks, so it is possible that some of them just deploy ingress filtering, this kind of solve mechanism on the routers and sublets belonging to them. But some other campus network may not do this.
I'll be honest, I think that's a very niche situation. I don't think that happens in a great deal of operator networks. If it's intra-domain, it's my domain, they're all my routers. If I haven't configured them properly, I think that's my problem. But okay, thank you for the clarification.
And Tony Lee got on the queue almost certainly to follow up on the same question. So Tony, you're next.
Actually, I have a different question.
Oh, okay. Well, go ahead.
Okay. I'd like to raise the BCP 38 question. Assuming you come up with a brilliant technical solution for this, how do we actually make sure it gets deployed and turned on?
So Terry, I'm not sure I get your question. So about PCP 38, okay?
Long ago, we solved this problem. We sat down rules and said everybody should turn on source address validation, right? This is BCP 38.
Yeah.
Some people did. A whole lot of people did not. And because not everybody did, we still have a world where everyone is forging addresses. Okay.
Yeah.
So
Yes.
how do we get it deployed? That's the real question.
Mm-hmm.
Okay. Given that we're accumulating a queue, I want to keep us moving because I don't want to get too far behind schedule. John, you're next. John O'Brien, you're next.
Hi, John O'Brien. Since I work at one of these institutions, one of these niche cases, where it's a highly distributed environment from a sort of an operations and management perspective, the way that I try to reconcile that practical reality with the sorts of models and definitions that we work with in IETF working groups, what I suggest is that we try to kind of reconcile it by treating the interdomain and intradomain as the sort of ideal cases, and trying to map our solutions onto one or the other, rather than trying to pursue these much more highly complex and varied organizational structures that don't necessarily align well to either one or both.
Okay, thank you for your comments. I think next we will discuss the interdomain case. Then maybe we can have a better.
We've still got another one on the queue. So, Dan, are you responding to John's comment or?
Yeah, I'm responding to John and to Tony. So first, I agree with John that we should, to the extent that internal organization things look like external organization things, we should try to align based on that. Because I may have internal customers who are part of my same company that I need to treat like external entities from a trust behavior. And so from that perspective, I need to go and align it more with that external domain side thing. And the second thing is, I do want to second what Tony said, which is that the reason why a lot of this stuff hasn't gotten deployed to date has generally been a lack of capability on the routers, or that there's a performance limitation on the devices that makes it such that it is either impractical or infeasible to deploy these. It's generally not a lack of the technical capability to configure it, but it's more that there is some other underlying limitation that has prevented operators from doing this in the past. Plus the fact nobody does it, and so when you encounter a bug, there's no incentive for the vendor to fix it. So none of this aligns with an incentive for how to actually correct the problem.
Okay, Dan, if you want to comment on the incentives, please do, and then we need to keep moving.
Yeah.
We've got about 10 minutes.
Yeah. Okay. So I just still want to make a brief comments on the discussions. I think there is BCP 3.8 and some networks make deployment, some others do not. I think we cannot have a very clear answer about what's the fundamental problem for these operators. Why some deploy and why some other do not deploy. But based on our discussions with some operators, actually the accuracy of existing mechanism and the incentive are indeed among the major concerns. And I think that there is a research paper this year. I cannot remember the exact conference. Actually, they made a good survey about a large number of operators, and just ask the fundamental reason of why the source address validation mechanism are not widely deployed. I think accuracy and the technology limits. I remember that they are one of the major concerns. Maybe next time I can just share their survey results. Okay. I just continue my presentation. So I just summarize the problems of existing Interdominant solve mechanisms. Including inaccurate validation, limited protection, and misaligned incentive. Next, I will just discuss the requirement of a new interdomain solve mechanism. Based on the discussions above, I think we have the following requirements for a new interdomain solve mechanism. The first requirement is that the mechanism must discover the real data plane forwarding path among routers in the interdomain network so as to avoid improper block under asymmetric routing. And the second requirement is that the mechanism must work for all kinds of interdomain spoofing traffic. For example, we should validate traffic from all directions. And if we can do so, we can block spoofing traffic as close to the source as possible. And the third requirement is that the mechanism must provide direct incentives so as to help deployed subnet mitigate reflection attacks from undeployed subnet. And the fourth requirement is about the cost. The mechanism must not induce too much overhead. For example, we want to avoid data plane packet modification, and we also want to limit the number of control plane protocol messages. And
Jared, did
finally,
you have another question? Yes.
Yeah. Hi, Jerry.
I have two comments on requirement number 2 and 3. I don't believe that it's possible for requirement number 2 or 3 to actually be a real world requirement. I don't believe it's possible for me to validate traffic from all directions, because if I'm facing the DFZ, I may not know what is a valid route to exist there. And for 3, I don't know how to create a direct incentive for somebody very far away to do the right thing.
So, Jerry, I'm wondering, you are
does
just
somebody else know? Because if so, I would love to hear it. But I don't see how these can actually number 2 and number 3 here can be actual requirements for a mechanism, because I don't see what the technical or administrative or policy thing could be that exists here.
John, you wanted to add to this? Didn't state your name.
John O'Brien, University of Pennsylvania again. I echo Jared's comments that I struggle to imagine how we can, treat these as requirements. I think they're valid goals, aspirations perhaps, but in the interest of trying to kind of stay positive and support the charter, I think another question it might be worth considering is whether we think it's possible to propose protocols or mechanisms that are probabilistic, or which could be more easily implemented, and so even partial deployment would still be an improvement over the current partial deployment of things like the BCP that's already been published.
Anything that could be an improvement is within scope for the working group to discuss.
Great.
And looks like Jared wants to get back on the queue. Thank you.
Yeah. So Jared Mach is depuring the network that originates the spoof packets a valid solution space? Because that's the only one I'm aware of, and I can think of a number of countries that may go offline as a direct result of this, because this is or networks, because this is what we see in the operator space. Is we know which networks are allowing a fair amount of this traffic through. And some of them are networks that it is not practical for us to actually do anything about, even if we know who the threat actor is for the real life use case here. So this is why I'm very concerned about trying to highlight 3 here as a requirement. Is, we often know where it's coming from, and there is no disincentive, including the potential, short of anything that might be kinetic, which is largely outside of the scope of the IETF.
Okay.
Dan, you have just a few minutes left to finish up.
Yes, but I still want to make some comments about discussion, because it is very important. I think we are talking about 2 different things. One is the requirement. The other is about the feasibility. So the requirement comes from whether we need it, and the feasibility, okay, is about whether we can do it. I think they are totally two different things. If we do have the requirement, but we do not have any feasible solution, maybe we can downgrade the goal. That's possible. But at this stage, I think we are just talking about the requirement. That is whether we need it. I think for requirement 2 and requirement 3, if we can come up with some feasible solution, of course we need it, because they can help or not. But of course we can downgrade the goal if we do not come up with a decent solution. So that's my consideration about this. And at this stage, I still want to put them as a requirement, because I think they are important for the operators. Yeah. Okay. So finally, I just give some preliminary idea about a possible solution. If we can just come up with a solution, I think in which we can discover the real data plane forwarding paths among the routers in the interdomain by via hop-by-hop prefix identification, and generate the SAF tables in the routers along the paths. Then each router can learn the real incoming interface for the source addresses of the deployed area. And in the data plane, the routers just validate the packets from received from all directions based on the local SAF table. And by doing this, it can protect the source addresses of the deployed area from being forged. Okay, this is a preliminary idea, and the more detailed solution maybe just will be discussed in the subsequent work of this working group. Okay, that's all of my presentation today.
First, I want to thank folks for coming up and asking questions and raising discussion, because that's what these working group sessions are for. So thank you very much. And Tom, you've got yourself in the queue. So if you want one more question before we move on to the next presentation, go ahead.
Hi, Tom Hill from BT again. As I understand it from reading this, I think what you're suggesting here is that when a packet arrives at a router, you learn where it came from and write it into the SAV table.
Yes.
Is that correct? Yes.
Yes.
So what happens if you have a compromised end host?
Yeah. You mean compromised router, right?
No, a compromised end host. So it starts originating traffic from an IP address that's not yours.
Mm-hmm.
You learn it in the SAV table and then trust it. Is that what that suggests?
Okay, Tom, it works like this. Actually, today I do not go to the details of the solution, because we are still the main focus is about the problem statement. But generally speaking, the idea is that when we learn the prefix, actually it just works among the routers. We do not directly talk to the hosts. It's still a network-wide protocol, just like routing protocols. So there may be compromised router or compromised router, but we want to do better than
I'm not talking about compromised routers at all. No, not a compromised router. You imagine you've got lots of virtual machines. They're in a data center. You've got a router. It's the first hop router. Am I understanding this idea is that when an end host, a virtual machine, originates a source, a packet, you learn the source prefix and you write it into the SAV table?
Let me just paraphrase Tom's question, Dan, for you. There is a specific case in here where you've got source prefix and incoming interface somehow being learned, known, whatever. And what Tom is asking is, do you simply assume all hosts are trustworthy and correct, or is there some other means, for example, knowing what subnet is supposed to be on a given interface, where the hosts reside, which you need to include as part of filtering what you accept from end hosts within your domain, because operators do have hosts inside their domain. And that's what's driving the question. He's nodding. And I think you'll need to clarify that when we get to the solution. We're not doing a lot of detailed work on solutions today. So I appreciate your raising it, Tom. We'll keep it in mind for when we get down to that part. And that may be something that has to appear also in the problem statement, is how do end hosts within an operator domain get properly secured, filtered, etc.
Yeah.
So it's a very useful question, but I don't want to go into the answer in detail now.
Yes, I mean it's the same notion as having routers that are unconfigured within a domain as it is learning and trusting end hosts. You can't trust anything. It has to be zero trust, or this doesn't work. Thank you anyway.
Very helpful. Very helpful. Thank you. Thank you, Tom. Yeah. We will consider it later. Yeah.
Okay, next presenter. Oh, whoops, no, there was one more question. Mackerman, sorry. Before I've got the next deck up, but you can ask, please.
Mike Ackerman. Dan, thanks for a great presentation and dealing with all of our tough issues here. On your solutions, your last slide, you talked about hop by hop. Does that mean you're using the extension header?
No, the solution as currently proposed by them does not make use of extension headers.
Okay, then that takes care of my real question. Thank you.
Okay,
we can come back later, much later, to how are we going to do all this, but that's not the current proposal. Okay.
Okay.
Nanqing, go ahead. You have slide control.
Okay, thank you. Can you hear me?
Yes, we can hear you.
Okay. Hello, everyone. I'm Lan Chengqin from Tsinghua University. I'm going to make the presentation for gap analysis, problem statement, and requirements of source address validation in interdomain networks. I will start with a background on existing interdomain cell mechanisms and introduce gap analysis, problem statement, and requirement, respectively, and finally, with a brief presentation of our preliminary idea for interdomain cell. Firstly, the background. Interdomain cell is important to identify and reject source address spoofing between ASes. To mitigate source address spoofing in the Internet, several sub-mechanisms have been proposed in IETF. They are IFC 2827, IFC 3704, and IFC 8704. IFC 2827 firstly proposes ingress filtering to defeat DOS attack. Then IFC 3704 further proposes several implementations for ingress filtering. More recently, in 2020, IFC 8704 analyzed the limitations of ingress filtering and proposed enhanced feasible path UIPF, EFP UIPF. IFC 8704 also makes the summary of recommendations for interdomain cell. For directly connected networks, the AS should perform ACL-based ingress filtering. For a direct connected single-homed stub AS, the AS should perform cell based on strict UIPF method. For all other scenarios, the EFP UIPF algorithm B should be applied on customer interfaces, while loose UIPF should be applied on provider and peer interfaces. This is an example of typical adoption of interdomain In this topology, there are 5 ASs. AS1 and AS2 are two customers of AS4. AS3 is peer of AS4, and AS5 is provider of AS4. Assume AS4 deploys interdomain. By following the recommendations of IFC 8704, AS4 applies loose UIPF on provider and peer interfaces and accepts source addresses existing in local FIB. On customer interfaces, AS4 applies EFP UIPF. EFP UIPF have two kinds of algorithms. They are EFP UIPF algorithm A and algorithm B. And algorithm B is the preferred one. In EFP UIPF algorithm A, each customer interface applies an individual IPF list, which maintains the acceptable source prefixes. In EFP UIPF algorithm B, all customer interfaces share a same IPF list. Now, I will describe the gap analysis for existing interdomain cell mechanisms. The first gap is improper permit. In this figure, we show an example of reflection attack. Reflection attack is a representative source address spoofing attack. In this interdomain network, the attacker in AS5 conducts reflection attack to the victim in AS1 by sending a request to the server in AS2 with a forged source address of P1. Assume AS1, AS4, and AS2 deploy interdomain cell. However, in this scenario, AS4 will improperly permit the spoofing traffic from AS5 because loose UIPF on the provider interface almost accepts any source address in local FIB. And finally, AS1 is attacked. Scenario 2 shows another improper permit case. In this case, AS2 forges the source address of another AS in the same customer coin of AS4. Assume AS4 deploys interdomain cell. If AS4 runs EFP UIPF algorithm A on customer interfaces, it can effectively block the spoofing traffic from AS2. But if AS4 runs EFP UIPF algorithm B, it will improperly permit the spoofing traffic from customer coin because EFP UIPF algorithm B allows source addresses of the customer coin coming from all customer interfaces. Therefore, existing interdomain cell may fail to identify spoofing within the customer coin.
Okay, before we continue, we have a question from Anthony Somerset.
Okay.
Hi, Anthony Somerset, Liquid. I'm just echoing a bit more of Tom's comments earlier. This is talking about misconfig of routers. Are we considering misconfig against, say, BCPs as in scope? Because it doesn't feel like it's new stuff here.
We're going to have to spell out the scope of what we want to solve and what we think can be solved. And there's a reason why in the discussion of the charter way back at the beginning, Aishan said, we will reevaluate things at each stage. If we conclude that the usefully addressable scope is not worth the work, we'll stop. But we want to do the analysis and see what we can do and then reach the conclusion rather than assuming. Go ahead, John.
Hi, John O'Brien, University of Pennsylvania. I'd like to just maybe phrase the question in a different way. Is this articulation of the gap saying that there is a gap with the existing documents?
Lancheng, if you'd like to comment, please.
Yes. Do you mean the spoofing within the customer core or the reflection attack?
Well, the slide we're looking at now says there's a case in which a router does something that it shouldn't do. Is that because the BCPs that are already published don't specify a way to accommodate this scenario, or is it because the configuration of the routers in AS4 is not sufficient to implement the BCPs?
Oh, well, in this case, AS4 runs EFP-UIPF algorithm B. It will allow source addresses from all customer interfaces. In other words, it will allow P1 and P2 from each customer interface. So AS2 can forces P1, that is the source prefix of another AS in the same customer core. This is because the mechanism of EFP-UIPF, it has limitations.
Okay, so this is a gap with the algorithm when correctly implemented. Thank you.
Yes.
Okay, keep going, please.
The second gap is improper block. Scenario 3 present improper block problem of EFP-UIPF caused by no export in BGP advertisement. In this interdominant topology, there are 5 ASs, and we can see AS1. AS1 owns prefix P1 and advertises P1 to its provider AS2 and provide AS3 respectively. When AS3 receives the route for prefix P1 from AS1, AS3 propagates this route to AS4. But differently, when AS3 receives the route for prefix P1, AS2 doesn't propagate the route for prefix P1 to AS4 because AS1 adds the no export community attribute in the BGP advertisement to AS2. In the end, AS4 only learns the route for prefix P1 from AS3. Here, we assume the forwarding path from AS1 to AS4 is AS1 to AS2 and to AS4. In this case, if AS4 runs EFP-UIPF algorithm A on customer interfaces, it will improperly block legal traffic originated from AS1 at interface 1. Because AS4 doesn't learn routing information to AS1 from this customer interface. Assume AS4 runs EFP-UIPF algorithm B. If AS3 is customer of AS4, AS4 will accept the legal traffic, so it is no problem. But if AS3 is peer of AS4, AS4 will still improperly block legal traffic at interface 1 because it doesn't learn routing information to AS1 from any customer interface.
Okay, Sriram, looks like you want to clarify something on this. Go ahead.
Yeah. Yes. So my comment is that when a prefix has a no export attached to it in towards one provider within the customer cone, it still wants to have reachability throughout the internet, I suppose. So P1 will announce AS1 will announce P1 towards another provider, and subsequently if AS1 is indeed in AS4's customer cone, then P1 will be received at AS4 on another customer interface. So in that case, algorithm B will work fine, and it will not improperly block. So I think it's a little bit tricky to say that an AS1 is in your customer cone, but it has no way of it has no path at all to the AS4 within the customer cone for this prefix. So it may use no export in towards one provider, but it won't use no export towards all its providers. That's my comment.
Thank you, Sriram. Igor?
Just to clarify what I believe Sriram is saying, that on this picture, AS3 to AS4, it says it could be C2P. So if it is C2P, then AS4 will hear it from a customer, and 8704 will work fine. But if it's P2P, then it is a problem.
Yeah, yes. If AS3 to AS4 is C2P, it's no problem. But if it's P2P, there will be improper block.
Okay, let's keep going. Oh, whoops. Sorry, I was going to keep moving, but Jared has another question on this slide. So
Yeah, it's more of a comment. So this no export example, I think, is a very valid example where people go and say, please don't advertise, please, AS2, please don't propagate my route to AS4. But AS1 may still pick AS4 as best path for reaching AS4 based upon if AS3 is down. And the issue here is quite often the packet validation behavior that you want the network to do is different from the routing behavior that you want networks to do. And this is one of the big gaps of why this is such a challenging problem space to solve. So in looking at this, I would argue, for example, that it's a misconfiguration of the network to set no export or to set no advertise, as opposed to using some other, traffic engineering community. And this is why no export is well known in the operator community to actually potentially be very harmful, because you can actually create black holes in the network whereby which traffic you'll create reachability issues and localize like blackout or brownout type situations where the network is not available as a result. And so this is something where I would say that this is perhaps not necessarily an improper block, because it is still a valid forwarding path from AS1 through AS2 to AS4. And so I don't believe that this example represents the network behavior that the end user would expect, because customers of AS1 reaching customers of AS4 or beyond may want to use that data path for forwarding, and if the traffic is then blocked, that would negatively impact them by denying them of service.
well, I believe what you said, Jared, was actually a little more nuanced in that it's if you do it this way to achieve routing objectives, you are liable to get validation problems. But maybe the right answer is don't use this tool to get your routing objective.
The issue is when one uses solely one direction of the routing information, unidirectional routing information, to build the filters that might get installed into the hardware for packet filtering. When you use just that single direction, you may get undesirable side effects. In this case here, traffic being blocked. And this is what triggers customer support calls. And every service provider out there tends to optimize their network on not receiving customer support calls And this is a very critical element when you come to the other, from the prior presentation about incentives for deployment. The incentive for a provider to deploy this quite often is there is not one, because you deploy it, you're likely going to break something and trigger support calls and require the customer to communicate additional information about what IP space is valid. So, like I said, I don't believe that this is an improper block, because you don't have the full forward and reverse path visibility to understand what the behavior is. And quite
It's an
often,
undesirable block, but maybe not an improper block. Anyway, thank you.
Yeah, I would disagree. But.
Dino?
This is Dino. I just want to echo what Jared had to say. You can't use the routing protocol to do forwarding stuff in the opposite direction. That's all there's to it. You'll lose asymmetry, and that's a feature we depend on the internet. You want asymmetric paths.
Okay, let's keep going.
Yes, the forwarding path is chosen by AS1, so it may choose the forwarding path and its propagation is routing in BGP based on local policy. Okay, scenario 4 shows an example of Anycast Edge Hybrid Direct Server Return. EFP UIPF will improperly block legal traffic in this scenario as well. Anycast is a network addressing and routing methodology, which is widely used in content delivery network. In practice, the Anycast IP prefix is usually announced only from Anycast server with lot of connectivity. When Anycast server receives incoming request from user, the request is then tunneled to Edge server, where the content is. Subsequently, Edge server will directly send the content to the user. To ensure that direct server return works, Edge server must send response packets with Anycast IP address as the source address. So in this figure, we can see Anycast server is in AS5, Edge server is in AS2, and user is in AS1. The Anycast prefix P5 is only advertised from AS5 in BGP. When user in AS1 sends request to the Anycast server, the forwarding path is AS1, AS2, AS4, and AS5. Then Anycast server.
Yeah, I'd like to let John ask his question.
Okay.
It's actually John O'Brien, University of Pennsylvania. It's an observation, which is I see a lot of commonality in the gaps we've analyzed for both the intra and interdomain cases. It strikes me as being substantially similar to the problem we faced when trying to implement policy-based routing based on source addresses. The problem is that every hop along the path has to have the same policy configured. And if one of them doesn't have the right policy configured, that's an operational problem that's going to cause routing loops, discards, things like that. The way we solve this for that scenario is to do things like building a mesh of label switched paths, which means that there's only one routing decision, which is the routing decision at the source and not on a hop by hop basis. I think the equivalent in my mind for this problem space is to recognize that the most straightforward places to implement source address validation are at the inbound edge, which is equivalent to a provider edge making a single routing decision for the entire path. That's it.
Jared, you wanted to comment on this?
Yeah, I just wanted to comment on what John said and add the fact of I haven't heard anything explicit here to say that we're talking about just IP packets versus label switch packets as well within this domain, and that we may want to, if we're going to really throw it open to everything, then Are we talking about when routers are processing non-IP packets as well?
I think there's a whole set of issues under particularly the intra-domain MPLS case that we'll have to come to when we do a more detailed analysis, but not for today. Lan Cheng, please keep going.
Well, I'll discuss our problem statement and the requirements later. Okay, let's focus on scenario 4. In this case, when edge server sends the content to user with the source address of prefix P5 to AS4, because AS4 never receives routing information for prefix P5 and AS5 from any customer interface. If AS4 runs EFP-URPF algorithm A or algorithm B, it will improperly block the response traffic from edge server at interface 1. The third gap is misaligned incentive. As mentioned above, for example, in scenario 1, reflection attack, and scenario 2, spoofing within the customer code, existing interdomain cell may improperly permit spoofing traffic. Particularly, even though the victim in each scenario deploys interdomain cell, the attack still succeeds. Moreover, existing interdomain cell is completely vulnerable to source address spoofing from provider and peer interfaces. Based on the gap analysis, we conclude the fundamental problems of existing interdomain cell mechanisms. We conclude 2 fundamental problems. The first problem is inaccurate validation. It means existing interdomain cell mechanisms have improper block or improper permit problems. It is because that they all conduct cell based on local RIB information, which may not match the real data plane forwarding path from the source. In other words, the complex interdomain topology, policy, and technology, such as tunnel technology, can make it difficult to achieve accurate cell only based on local information. The second problem is misaligned incentive. Networks would still suffer reflection attack even though they have already deployed cell mechanisms. It is because that in existing interdomain cell mechanisms, the victim with self-deployment doesn't participate in protecting its source addresses from being forged. To narrow the gap of existing interdomain cell, we define several requirements for new interdomain cell. The first requirement is, the wording is wrong here. It should be must. I mean, the cell mechanism must discover the real data plane forwarding path among routers. In this way, interdomain cell can avoid improper block and reduce improper permit as much as possible. Because this requirement cannot be met by using local information, additional control plane mechanisms are needed to deliver the required information. The second requirement is the mechanism must provide direct incentives. It must help the deployed area mitigate reflection attacks from undeployed area and support incremental deployment. The third requirement is the mechanism mustn't induce much overhead. To save communication and computation overhead, interdomain cell must avoid data plane packet modification and limit the number of control plane protocol messages.
I will note that many of the questions that were raised on the previous requirement slide apply also to this requirement slide and will need to be discussed further in the working group, but they clearly apply. Lanching, we're out of time, so I don't want to go into the solution proposal for this because we are short of time and we have promised other people some time. So I want to just recapitulate where we are. Before I do that, I want to make a suggestion to people. We've had a really good, engaging discussion. As a result, the minute taker has not managed to capture all of the important points. They've been trying. So I would suggest you go into the tool, and if you just tell it that you log in through the data tracker, it'll let you edit and make sure that it's captured your points accurately as you stated them. No, don't try to elaborate, but just let's make sure we get it right. That's the best way, is if you check it right now while you remember what you said, so that we make sure we have minutes, because given the very useful discussion, I don't want to lose that. Now we're going to move on to 2 more presentations. Just a moment.
Okay,
and we'll
thank
get
you.
there. The first one is going to be a combination of more problem and analysis and a description of an approach that has not been brought forward during the BOF that the chairs felt that the chairs were asked about and felt would be useful to be presented. So we're looking forward to that. On the interdomain, and that may bring up again additional requirements or problems that will help people inform the gap analysis. And then, assuming that the discussion doesn't run too long, and we will give time for discussion, there will be one more discussion of an alternative solution for the intradomain space. And that is presented just for information, just so that you folks can say, well, if you wanted to consider that, that would raise this other problem or this other gap that needs, or this other requirement, so that we can get things considered at the proper phases. We're not going to debate whether the proposed solutions are the right solution or good solutions, but we will be going through what they are. So now, there. Igor, the microphone right here. I will drive your slides. Just let me know when to change.
Can you guys hear me? Awesome. All right, I'm Igor Lubashev, and I'll talk to you about some of our thoughts.
Okay. Meanwhile, while he's checking the power, David Lamperter had a question.
David Lamperter. Sorry, it was an agenda item to discuss the working group direction, and my comment was for that. I'm seeing a lot of confusion in the previous discussions here that, from my perception, is stemming from a perspective that is not helpful in attacking this. And I would like to suggest a slightly different perspective at this issue, which is to, instead of trying to construct this perfect filter, what this is trying to achieve is defense in depth. And if you start from a perspective of defense in depth here, then a lot of the scope questions and which router do I trust, what is going on, a lot of these questions become completely irrelevant. And from that perspective, what I would like to answer is, for whatever specific router I'm looking at, what can that router do to help? That is not necessarily a 100% perfect filter table, but rather what sources can I make statements about and maybe generate some filters for that. That is a much more, I think, productive question to ask, and might help to push this forward.
That is a definitely interesting question. Thank you. Sorry. Okay.
All right, that thing is working now. I can hear myself. Okay, great. Igor Lubashev, let's go to the next slide. This slide you've probably seen now. It's the third time you're seeing it. So I'm not going to elaborate, except to say that two things. Well, few. No, not that fast. Can we go back? Thank you. So first of all, the problem's been with us for 22 years. It's been understood from BCP 38 in 2000, and so the approaches that been tried before, that been used before, is essentially looking at BGP update message and trying to divine some information from the reachability signal. So feasible path, we've seen the problems with it. It works great, except in real world, where you have multi-homed network with some sort of traffic engineering that involves route filtering. In 2020, we have 8704, which still looking at BGP, but has a little interesting. Oh, sorry. A little interesting idea where you also look at the originating AS number and say that, well, even if I have not seen the prefix, if it shares an AS number, and if I learn it from anywhere, not just necessarily your customers, but anywhere, I will accept it too, as long as I've learned that at least one prefix is originated from that AS number and coming from pointing towards my customer interface. And that's better, but it still has problems. We've seen it before. Also, that RFC has mentioned in one short paragraph using RAW to augment that information, but it's almost like in that RFC, it's almost like an afterthought. It doesn't go into the details. All right, and we're here at 2022 talking about it more and even have a working group for it. Now, next. So that's a very similar example to what we've seen before. It's just an example where 8704 doesn't work. You have an AS1 that is a customer of AS2, and AS2 is advertising its customer prefixes to both of its providers, but its own prefix only to one of them for reasons. And so AS4, when it's looking at the customer interfaces, looking at all the BGP prefixes, it doesn't see AS2 in the source, in the origin AS number, and therefore doesn't accept any of its prefixes. Oops. So anyway, and that's been also said, why is this problem so hard? And I agree with like that. Basically, it's so hard right now because we're trying to infer data plane forwarding paths from information and signal that was not designed for it, BGP. Okay, next. And this is an example. I'm glad that we already kind of seen it before. It's pretty familiar to me because, and I immediately apologize for the slide. It took us from internal presentation. It's a little bit more graphic than we're used to at IETF. Or let's say it has more graphics than we're used to at IETF. It's Anycast CDN case where CDN wants to use an Anycast IP address located in, call it Anycast home pop. User connects there. The home pop figures out where the best edge location is to serve the particular content and want to serve it from that edge location directly to the user. It's a pretty nice setup. All the bulk media download happens direct from the edge location to the user, and only the small headers and eggs take the detour through the Anycast pop, where they're tunneled probably in some sort of AP and AP to the edge. Next. And this is a just generic direct server return, more familiar diagram. You have AS1, which is a Anycast pop owned by CDN. AS2 is an edge pop, and user from prefix 4 sends the request, sends the packet, establishes a connection to prefix 3, which is Anycast prefix, lands in the home pop, AS1. AS1 tunnels to AS2, AS2 replies directly to the user and AS2 has to send packets that claim to originate from prefix 3, which is never advertised. And the question is, will its provider, AS9, if it does any sort of validation, accept it? And DSR has many use cases. This CDN thing is one of them: mobile roaming, low latency gaming, security products, more. So it actually is useful technology. Next. Just for fun, some stats. In 2015, when we built this product at Akamai, and we've measured it from several thousand POPs around the world, and we figured that about 15% of locations of networks around the world, or at least POPs, maybe some of them are in the same network, they do some sort of source address validation. And just before coming here, I pulled the stats. And in 2022, about 15% of the locations do source address validation. So 7 years, the needle moved none. Could it be economics? Or possible, but I would not entirely explain it. Small networks actually benefit from blocking attack traffic and not paying for it. It could be that SAV today is just not effective, or basically generates too many service calls. Could it be that 8704 would do better with more adoption? Maybe. But given that it also has problems, maybe not. So can we do better? Again, the requirement for solution, we've seen that before. It's nothing too different. Definitely, we need to, first of all, make things better technically. Otherwise, what kind of solution is that? And it has to offer, very important, has to be deployable. It has to offer immediate benefits to early adopters for whom the cost should outweigh, should be lower than the benefits, right? We already said it kind of would be very nice if it also incentivized non-early adopters to adopt it later when a bunch of people have already adopted it. I mean, Jared's point is, how can you incentivize somebody far away? So it's nice to have. But what's important to have is it has to be easy and friendly to do for small networks, because that's where most of the filtering is required. That's where most of the filtering is most effective. Next. So our way of looking at it, we call it bar SAV, which is basically means our protocol is looking at BGP update messages like state of the art now, but augmenting it with information from ASPA and RAW. So first of all, it's just strictly an improvement on, even if you don't have RPKI information, it is better, making a better use of ASPath information that's already there. 8704 just looks at origin AS. BarSav looks at every single AS number on the path and uses it as a signal. And also it augments it with some additional source of information that's actually secure and authenticated and stuff. So on one hand, it's still using signal that for a purpose that it was not designed for, so BGP and RPKI. But on the other hand, it doesn't require any protocol changes on the wire at all. It uses all of it already there, and therefore it offers immediate benefits to the adapter. The very first network to adopt it would reap some benefits. Next.
Before we go to the next slide, Antoine Verschuren asked a question in the chat and asked it to be relayed. Is it useful, practical, possible to include using accurate IRR data in this method? Would that help?
Good question. So Sriram here is as well. He's a co-author that he might also have some more input on that. And yeah.
Go ahead, Sriram.
Okay. Yeah, I think since the RPKI is already in place and the adoption is growing, especially for route origin validation, the IRR data people have been hesitant to use because of the lack of reliability. But the RPKI-based ROA and the ASP has not the adoption has not begun. The draft it's still a draft, but the hope is that in the coming years, next maybe 4 to 5 years, ROAs as well as ASPs will be in place, which are authenticated and far more reliable.
Okay, go ahead.
Thank you. All right, so this is a busy slide with lots of circles, but its only purpose is to show that the algorithm can be absolutely equally applied to both customer interfaces and lateral peer interfaces. So next. Okay, so this is again, we're not trying to describe the algorithm in detail, but here, but the general overview of how it works is a two-phase algorithm. Phase one is discover customer cone. Phase two is once you discovered AS numbers in a customer cone, discover the prefixes that you should be including in your SAV filter list. So, how to discover customer? Thank you. Okay, great. So how do we discover customer cone? We start with the only one AS number that we know, which is the AS number on the other side of the interface in question. And then iteratively, we look at ASPA data and see if it's a customer or if any AS in ASPA lists this AS as a customer. And we also look at our BGP update AS path that we have. We look at all of them, no matter where it was learned from, no matter which interface, and see if any of the paths have this AS number and see which one was the previous one. So from that information, we may discover a few more AS numbers, and then we repeat it iteratively for every single new AS number that we discovered. And when we have learned, when we've done this iteration and have learned no new AS numbers, we're done. So we have the list of AS numbers that are part of the customer cone. Once we have that, we look at raw information and see which prefixes have been announced, declared through raw that these AS numbers can advertise, and we include that in your sublist. And then we look at BGP update messages and see for which, again, no matter where it's, the message originated from, no matter where it was learned from, we look at all the messages that have origin AS numbers in the customer cone list and include those prefixes. So merge the two lists together, and this is your SAV list.
Jared?
I'll bring this back to you in 1 second. Sorry. So in the case that there's a large prefix that's part of this customer cone, let's say a /12, and there's off-net holes in that prefix list, are you going to build the list of the holes within that supernet when doing this, or is this just a CIDR roll-up of everything that exists within that table?
So right now in the draft, as it is, it's a roll-up of everything that's in the table. more ideas are definitely welcome. I mean, this is just a draft. That's the first time we're bringing it to IETF. All right, very good. So this is back to our example that we've seen before, and the one that 8704 could not discover AS2. Now Barsav definitely discovered AS2 during its customer cone exploration. I mean, it was trivial in this case. The previous presentation, we had one more AS between AS2 and AS4, but it doesn't matter. It would have been discovered during the customer cone exploration, and then you see there is a prefix announced through the peer, and it has AS2 as an originating AS number, and therefore prefix 2 is included in the sublist. And we have Ben.
Ben Madison.
Thank you. Ben Madison, Work Online. So I think this makes sense. I think using the whole of the AS path makes sense. My concern with respect to the use of the RPKI stuff is that all of the current uses of that data assume that nothing, they're constructed on the principle that nothing breaks if those objects go away. And in this case, the filters will suddenly get stricter if a bunch of ASPAs or ROAs somehow blip out of existence. And that's going to be a lot of support calls and a lot of very hard diagnosis work, which I'm not thrilled about. I think if you could authenticate it better, IRR data would actually be a better fit for this because it doesn't blip out of existence in the same way, but it has a whole bunch of other problematic properties.
I don't want to spend too much time on details of solution. I appreciate raising the issues, particularly the consequences of relying on this data that may go away. Very important part to keep in mind, but we're not going to explore the full solution space today.
Yep, thank you. Yeah, so definitely it's a concern for the implementation. I mean, there could be a reason why it goes away, and maybe it's a good reason, and it should, but definitely a temporary go away should be dealt with by the implementation. Okay, next. All right, and now we're looking at the CDN example again, and now we know that the CDN owns AS1 and AS2, and it owns prefix 1, 2, and 3. And what CDN can do is it can publish raw information, allowing AS2 to advertise prefix 2 and prefix 3. The 3 is the anycast one. Now AS2 has no intention to ever advertise prefix 3, but it is in raw, and therefore if AS9 uses bar7 and pulls raw information, it will allow the DSR. Next, and we're done.
Good. So any other questions for this presentation? Okay, thank you, Igor. We will go to the last presentation.
Right.
Sriram, you wanted to add something? You know, first Dan and then Sriram.
Just a quick comment that in the CIDR ops, we will be presenting this work in much more detail, just in case someone is interested to hear that.
I'll just add that the backup slides that are available, you can download and read them, have a lot more detail too.
I appreciate your structuring the deck that way. Dan, you wanted to add something?
Yeah, my general question is that maybe the bars of does not solve the problem of the possible spoofing traffic from the provider direction. But okay, that's more about the solution. Maybe we can discuss more details by mailing list later because the time is limited. Yeah.
Okay, we now have one more presentation. This is very much a solution presentation, but observe it from the perspective of trying to see what other potential problems or gaps or requirements should we take into account during the first stages of the work? Whether or not this is the right answer is a different question we'll get to. With that, I don't remember which presenter is going to present it. Okay, Yang Zheng. Go ahead, Yang Zheng. I'll give you slide control.
Hello, can you hear me?
Yes, we can.
Good afternoon, everyone.
You have slide control. You may advance the slides.
Can you help me to turn the page?
Huh? I didn't hear that.
Please repeat. I can do it. This is Yuanxiang Zhu from New H3C Technologies. This presentation is on a method of source address validation in Interdominant. This is a zero version individual draft. This is the background of the draft. The SAVNet Interdominant problem statements describes the current problems of sub in domain and the requirements for solution. Based on the requirements of sub and some achievements of the work group, we propose a method to calculate sub information independently by each router by extending IGP. The sub information can be used to verify the legitimacy of the packet source address. We propose this draft and these ideas to share our idea and these slides to share our ideas. Sorry. To see if
tell me what slide, Yanxing, we lost. You weren't advancing your slides. I have taken slide control. Just tell me what slide you want me to be on as you go through.
Okay, thank you.
Currently sharing your terminology slide.
Thank you. This is the terms in this draft. First is sub information. Bounding entries independently calculated by the router that enables sub function. Its context include prefix and incoming interface. In order to distinguish from other advertised prefixes, we call these prefixes that participating sub calculation advertised through IGP as protected prefixes. Redirected forwarding process, such as PBR or QS, the forwarding path of the packets processed by these prefixes can be consistent with the routing table. Next slide, please. Thank you. This is the overview of the proposal. Advertise the protected prefix through IGP. Calculate sub information according to the received prefix and determine the incoming interface to achieve accurate source address validation. When the router advertises prefixes, it identifies the protected prefixes. For other routers that enable sub function, need to calculate sub information according to the extended routing message. Here, IGP needs to be extended. Currently, ingress filtering can be achieved by deploying URPF. The URPF uses the source address of the packet to look at the local fib and determines whether the packet is valid according to the lookup result. However, the local route table is used to guide how to go from the local to a node where the source address is located. It cannot really reflect how to reach local. Therefore, the local fib cannot be fully trusted to validate the source address. We believe that the calculation of SAV should depend on the routing table of other routers. Next, I will introduce the calculation logic of this protocol in detail. Next slide, please. Thank you. Use this figure to introduce the calculation method. The subnet prefixes accessed through R1 to R5 are P1 to P5, respectively. And these prefixes act as protected prefixes. Take R3 as an example. How to determine which interface the packet from the source prefix will arrive at R3. From the packet received by R3, there's a common feature. That is, R3 is the next hop or intermediate hop in logic. If the packet comes from R1, the forwarding path to R3 is determined by the shortest path tree with R1 as the root. Therefore, R3 need to calculate the shortest path tree in tree R1 to calculate SAV. Next slide, please. The calculation process of R3 is step 1. Calculate the shortest path tree with R3 itself as the root. Step 2. Take R routers who advertised the protected prefix as the root to calculate the shortest path tree. Calculate the legal incoming interface for prefix P1 based on tree R1. On R1, the tree R1 interface 1 is connected to the upstream node of R3. So interface 1 is the legal incoming interface of P1. The legal incoming interfaces corresponding to other prefixes can also be calculated in the same way. Next slide. Next slide, please. Next slide, please. Thank you. This is a problem of inaccurate sub-information calculation in scenario of inter-area, referring to the topology in the figure. Continue to take R3 as an example. Due to the inter-area advantage of root, R3 cannot be aware the cause of the link in area 1. According to the root, R3 will calculate that the legal incoming interface of the packet from P6 is interface 1. But in fact, this is wrong. Based on the actual course, the packet from P6 will reach R3 through R5. The really incoming interface should be interface 2. So, how to solve this problem? Our solution is extending IGP, carrying the total cost of prefix to ABR when ABR advertise inter-area router. When ABR that enables sub function advertise network summary LSA, ABR calculates the total cost from R6 to ABR and advertise the total cost to R3 through protocol extension. That is when R4 advertise the prefix of R6, it carries cost of 10 and reverse cost of 100 at the same time. Similarly, the cost of P6 advertised by R5 in two directions is 14 and 50. R3 then determines the real incoming interface according to the reverse cost. Next slide, please. Thank you. This is the extension of prefix sub-TLV for IGP. It is used to identify protected prefixes. For ISIS, the prefix sub-TLV is the sub-TLV of the following ISIS TLVs. The prefix sub-TLV contains through fields, type, length, and flag. The flag is a reserved flag field, which is not defined at present. OSPF v2 and OSPF v3 need to be extended accordingly. Next slide, please. This is another sub-TLV extended by IGP for SAR. Coding prefix reverse cost sub-TLV. It is used to carry the total cost from the route where the prefix is located to reach ABR. The prefix reverse cost sub-TLV contains three fields, type, length, and the reverse metric. The reverse metric field fills the total cost. OSPF v2 and OSPF v3 also need to be extended accordingly. Next slide, please. This is about some considerations of the redirected forwarding. In the actual deployment, some redirected forwarding process may be used, such as PBR and QoS. The process forwarding path may be different with IP routing paths, resulting in additional incoming interface. The source address, destination address, or some other non-address fields of the packet can be specified as metric characteristics. In order to achieve more accurate sub-information calculation, IGP can be extended in the future to advertise the redirected forwarding process to our routers. Next slide, please. The redirected forward. Okay, next. This is the next step. First, analysis on redirected forwarding process and protocol extension. Further analysis about backup paths. Keep the terms consistent with our drafts. Any questions and comments?
Okay,
thank you.
Anthony? And David, you might as well move up to the microphone after him.
Hi, Anthony from Liquid. Just the one observation from the slide decks, and if in the meantime you could go back to the one about the costs on the protocol extension. This solution again is fundamentally reliant on the BGP that you're getting from your being, trusted, which is not necessarily a good thing. I think where BarSav at least was like, let's get some external validation. Yeah, so I just wanted to, there was, I think it was a bit further back. It was talking about extending to track the total cost, which I'm like, does that even necessary? Because you're going to,
that's, I know which slide you're talking about.
yeah, there you go. The total cost of the prefix to the ABR. And I'm thinking, can't we already calculate that anyway? We don't need to do any extension to do that.
I believe that they are correct that it's not actually visible in the current routing system, the remote cost.
Okay.
And the other point I will make is that the question of BGP dependency, we've said we're going to separate intra-area from inter-area. Intra-area operates on the assumption that the inter-area is correct. That may not be a valid assumption, but we need to keep our problems separate or our heads will explode. David.
David Lampotter. Have you considered not, so this is trying to determine the one path that packets will come from for any given source. But without going through all this work, there is a lot of situations where we can know all paths that a packet can come from. And those all paths are not necessarily all interfaces on a router, which would already allow us to restrict inbound traffic for that given source prefix. So has there been any consideration of what is already doable this way?
I think we need to see a draft which described what could be done. It's a reasonable question. It's just, I don't think anybody's said that could let you handle this kind of cases. Go ahead, Jared.
Yeah, Jared Mach, Akamai. So similar to my question for Igor earlier, a lot of cases we see a route summarization of an aggregate route, like a /24 or something, where we go and we roll something up either in an IGP or in an EGP, like BGP, where we'll go and we'll have a /24 and a bunch of 31s, 32s or something that may live within there, and they end up in either different areas or something like that. How are we going to do this without going, because this is done to prevent the CPU scale of the router from being blown out by carrying all of the state, by creating the summarization, to some extent. Jeff's shaking his head, but to go and create some amount of summarization where some information gets rolled up and aggregated. How are we going to do this, without going and creating the exact same problem that we're trying to prevent in limiting the routing domain? Like, how is this protocol going to scale differently if it's designed than any of the other existing routing protocols that we've built so far?
I think the
do we have an idea?
question is more nuanced than you asked it, but there is a very important question in there. If you have to get this remote information and it is aggregated, but the aggregate is not going to be accurate, so you have to disaggregate, did you just blow your whole scaling system up? And that's an important question to figure out if any of these approaches will work.
Yeah, and this is what operators face on a daily basis, because we're left with devices that have limited hardware space to program filters, or limited hardware space that actually will take forwarding table entries on which to do something like a RPF check or similar.
Yan Singh, you wanted to comment?
Okay. Okay, comments I have received. We will continue to analyze the solution in the next version.
Okay, thank you. And thank you, David. You've got some interesting notes in the chat that will need to be considered before we are done. Definitely. Aishan, did you want to make any closing comments before I let everybody go? I guess my co-chair doesn't need to add anything. I very much appreciate the discussion and engagement. That's what working groups are for. Thank you very much for your time. We will see you on the email list.
Hello.
How's it going?